Hello and welcome to this walkthrough of the mock RPA exam for 2016. I just want to point out a couple of things. It shouldn't be treated as a mark scheme. As I put on the screen, the official OCR mark scheme always needs to be consulted first for the correct guidance from the exam board, because the mark scheme has been created by a set of professional examiners after a rigorous exam board meeting where all of the ideas and guidance that are in the mark scheme are agreed between the markers themselves and the chief examiner. What this clip is really for is to try and develop deductive and recall skills. So whether you're looking at this a year after the paper was taken in 2015, or whether you're looking at it quite some time after that, ideally you'd need a copy of the paper in front of you. If you took this as your mock, then a copy of your script would be the best thing to have in front of you. And the way to approach it is to how you could recognise where application could have been used or recall could have been drawn upon from your revision, so that therefore you can take those skills and apply them across to an exam paper that you haven't seen yet. That would be the most useful way to use this clip. So assuming you have the paper in front of you, I'm going to make a start. So this one introduces by talking about gas chromatography, and then followed by mass spectrometry. When I was marking the script, I noticed a few people started talking about ways in which you'd use the mass spectrometry. You're not actually asked about the mass spectrometry at any time during this question. So it gives you two components. Obviously they're phenol compounds, phenol-based compounds. One has an ester linkage. Does it? No, it doesn't have an ester linkage, sorry. It has an ether linkage, compound B. And compound A has an aldehyde. Now you don't have to know about ethers, so if you're thinking, hang on a second, we haven't done that, that's true, you don't have to know about ethers. But it doesn't mean they can't show you an ether style compound. So the ether link, the ether linkage is basically this. This bit here is the ether linkage. But like I've just said, you don't actually have to know what an ether is or any of its chemistry to be able to do this question. It's just giving you a structure and asking you to think about gas chromatography. So it says the column in the gas chromatogram is packed with solid beads coated with liquid polymer. And it says, how does gas chromatography separate the compounds in the mixture? The two most important words here are how and separate. So that actually means at atom and molecular level, what determines the separation of the compounds? Not the fact that they partition, or perhaps not the fact that they separate out, but how does the separation actually take place? So what we're looking at is relative solubility of the two components. So the solubility in the two phases, the mobile phase and the liquid phase. So let's now look at the next part of the question. Very important thing on this question that I think perhaps a lot of people missed is it's the mass spectrum of the first compound to emerge. Now I know I may have mentioned earlier that the question doesn't ask you quite so much about mass spectrometry. This is a bit that deals with mass spectrometry, but most people that I marked, I think everybody actually managed to put something down that got them one mark at the bottom. I'll come back to the idea of trying to determine whether it's mass spectrometry or gas chromatography that they're asking you about a little bit later on in this question, because there were a few examples where it got a bit confused. But I'll come to that at the time. So it obviously says identify the compound responsible for this spectrum. Now the easiest way to use a mass spectrum to identify the compound that it's for is to look at the M+ ion, or the molecular ion. So in this case, the molecular ion is here. So what you can take from this is essentially the MZ, M over Z value, is the same as the MR in the case of the molecular ion. So what you do at this point is go back to the top of the page and you ask yourself which of compound A or compound B has an MR of 124. So I'm assuming that you've got the paper in front of you, so you have the compounds printed in front of you. Now would be a good time to pause if you didn't get this right and quickly count up the number of carbons, hydrogens and oxygens in each of the compounds. So most of the scripts that I marked had something along these lines, making reference to the molecular ion and saying it must correspond to the MR of compound B, being 124. But the important thing is that, I don't think anyone actually missed this when I saw the scripts that I marked, but in case you didn't get it, it could have been that you didn't say a reason for your answer. That's why I've highlighted the word because. Because if what you've put doesn't have the statement of the correct compound plus the reason, you don't get the mark. So it's, even though it's 1 mark, it needs the statement plus reason. So this would be an obvious example of reading the question. Okay, so let's go on to the next page. So it says, what does your answer to B part I? Now B part I is the one you've just written. Suggest about the interaction of this compound with the phases present in the column. So sometimes people got this question a little bit mixed up. You need to stick to the idea that you're talking about the solubility. Now the correct answer is that compound B is less soluble. So looking at the question, it talks about the phases. I would suggest that you'd need to be specific about which compound interacting more with which phase. In other words, you need to be specific. Whatever you do say, make sure it links the correct compound to the correct phase. So you don't have to say compound B is less soluble. You could say compound A is more soluble in the stationary phase. You could say compound A is more soluble in the mobile phase. Or you could do the reverse argument with the stationary phase. So there's obviously technically 4 different correct answers you could say, isn't there? But they need to be based around one compound being less soluble in one phase and more soluble in another, and it needs to be the correct compound. So don't forget that they told you earlier in the question which compound emerges first. That's going to be the compound that is more soluble in the mobile phase. And it said, I believe, I'll have a quick look, it said, yeah, the mass spectrum of the first compound to emerge was shown and you deduced that it was compound B. So that leads into this particular question. So that's the part, using the deduction, your deduction you made. If you use that correctly, then what you're doing is using your answer to B, suggest. That's the part of the question you're paying attention to now. Okay, the next part of the question is a reaction scheme. And it talks about forming an ester, doesn't it? So you can see you've got an aldehyde group. So we're talking now about compound A, so we're talking about the other compound, not B anymore. So let's move the page up. The basically what it asks you to do is to complete the boxes, as it says, putting the correct reagents in, or the correct compounds in. So in the first box, where it says reagents, you're obviously changing this functional group into this functional group. So in other words, an aldehyde is being oxidized into a carboxylic acid. So you want something along those lines, or dichromate ions, or Cr2O72-. You don't have to put it exactly the way I put it down there, but essentially that's what they're after. So provided you don't deviate chemically from what that says, you'll be fine. So thinking now about the ester is obviously going to have a combination of this compound and the reduction, because you're using NaBH4, of this compound. So that's what you need to think about. So if you start by reducing the aldehyde in compound A using NaBH4 to a primary alcohol, you now have your two feedstock compounds, compound C and the carboxylic acid you get from oxidizing compound A. So the flowchart leads you to the ester box, and the ester box you should now have a structure like that. Now obviously, as OCR always say, you can use a combination of styles of formulae, so structural, skeletal, etc. But provided there's no ambiguity and it's clear what you're trying to say the structure is, you'll get the marks. If there's ambiguity or confusion, in other words, could it be misconstrued or misunderstood as another chemical, then you're in trouble and you won't get the mark. So that would be the guidance to follow. So the next thing is to give the mechanism to show the formation of compound C. Now, like we said, it's a reduction. So obviously what you're thinking is nucleophilic addition using the hydride ion, because that's the mechanism that this compound, the reducing agent, actually uses. So let's move it down a bit. So it asks you to use curly arrows and relevant dipoles, reading the question again. So provided you've got something along those lines with all the correct curly arrows, the correct dipoles, and the correct structures, you will get your 3 marks. Now let's go on to... just remember, before we go on to the next page, I forgot to mention this right at the beginning when we were doing the oxidizing agent. So if we look at the fact that the aldehyde is being oxidized, alternative and legitimate oxidizing agents could be things like Tollens reagent or dichromate, sodium dichromate, or you could say acidified MnO4-. So apologies for not mentioning that a few minutes ago, but yeah, you could also use Tollens or acidified MnO4. Any legitimate oxidizing agent like that you come across at A level. So it says 1 mole of compound B reacts with 2 moles of bromine, Br2, by electrophilic substitution. It says write a balanced equation, so they don't want a mechanism, they want the equation. So what you should have put, and I think most people did, is something like this. Okay, in a small number of cases I saw people put H2 as an alternative side product instead of HBr and substitute all of the bromines on there. But it doesn't quite work out like that. With phenols, which this is an example of, You can substitute bromine on anywhere, so it doesn't matter where you put the bromine on. But the thing is that HBr is always produced when you undergo electrophilic substitution, which is why they suggested in the answer electrophilic substitution. So therefore the HBr has to come from your 2 moles of bromine. So you've got 4 bromine atoms, 2 of which end up on the phenol ring anywhere, and secondly you have 2 HBRs that have to be made, so the other 2 bromine atoms will end up there. So moving on to question number 2. A surprising number of people struggled with this one, even though it's basically recall. So you need to go right back to what you would have learned the previous summer, and that would have been when you first started doing A2 work. The first thing we started off with was teaching you benzene and aromatics. So it's very important to read the question here, and it says, with the aid of suitable diagrams, not diagram, so 2 diagrams, one for A and one for B. You must have orbital overlap in them, so don't just copy out structure A or do it in a slightly different format such as displayed formula. You've got to show the orbital overlap to get the first mark. So those are the 2 possible options that you've got, but you've got to draw the orbital overlap somehow for both structures. So there's 2 different styles that are acceptable. The bottom style is what's in the textbook, but the top style is okay as well. Any attempt to show that you understand that there's orbital overlap going on in your diagram must be in there, and it will be credited, provided you do it for both structures. I saw some examples where people didn't do it for structure A. So if we now move the page down a little bit, we can then talk about what to actually say to back up your diagrams. So, in structure A what you've got is localized electron density between pairs of carbon atoms. So each carbon is part of a pair where there's double bonds taking place. We need to say a bit more than just double bonds. We need to say what that actually means. So for structure A, like we just said, localized electron density between 2 carbons with sideways overlap. So I'm still making reference to orbital overlap because it's highlighted in the question at the top of the screen. So I've just added in that the overlap of the p orbitals in structure A would be called pi bonds. You can actually use the symbol pi, but I'm not sure if the app I'm using actually has it. So I'll just put it in words. So pi bonds are formed from sideways overlap of p orbitals again in structure B, but this time the electrons are delocalized around the entire ring. So that's the kind of language they're looking for, not just it's got double bonds or it hasn't got double bonds. So things like delocalized are what they're after. So you'll see that I put localized and delocalized in there. That could be the appropriate technical term they're after up here, spelled correctly. Okay, so let's go to the next page now. So this time we've got some enthalpy changes, and obviously one of them you probably spotted already is to do with benzene, which would be compound B, or structure B. So it says using this information. Whenever they say using this information, that means you've got to refer to what they've actually said and given you. Don't just make statements that happen to be correct, but which don't refer to the data. So the people who did that were the people who got 2 marks. Okay. So using the data you can work out that structure A has an enthalpy of hydrogenation completely of minus 357, which is more exothermic than that of structure A. So therefore, I need to change my answer slightly there, actually. There you go. So you need to make reference for 1 mark to the data. So the minus 357 shows that you've actually done that. And the statement that structure B is a better representation of benzene because it is more stable shows that you understand that the minus 208 enthalpy change of hydrogenation as opposed to the minus 357 enthalpy change of hydrogenation means that a less exothermic enthalpy of hydrogenation would mean the compound is more stable. So you know that, or you should know, that benzene is more stable than the calculate structure, which is the representation in structure A. So this is an application of your understanding of calculate evidence. So let's now look at the next part of the question, which is about an application of mechanisms or understanding of mechanisms. Okay, so this part of the question is very much an application question, because obviously you haven't seen this particular mechanism before. But what it does tell you is that benzene compounds can undergo nucleophilic substitution reactions. Just because it's not in the textbook doesn't necessarily mean it doesn't happen. All that means is it's not on the specification. So this is obviously a deductive question. So what you will need to remember is what actually a curly arrow is in a mechanism. What does it mean when a curly arrow starts somewhere? What does it mean when a curly arrow points somewhere? So the correct answer here, I'm just going to get my work out to myself. Bear with me a second, the shuffling of papers in the background. It's something like this. So you have the nitrogen and the aromatic group having a bond, and that breaks. And then the fluoride ion, being a nucleophile, comes in and attacks the remaining positively charged aromatic ring. So if you have a quick look at what I've done to annotate it, what I'm trying to do is explain how you can work out, from deducing what bonds are broken and what bonds are made, where to put your curly arrows. So curly arrows should always originate from either a bond, which is an area of electron density, or from a lone pair, which is another area of electron density. They should always point towards either positive charges or a positively charged species. So for example, in the second curly arrow, it's pointing towards the positively charged carbon. I've pointed it towards the actual positive charge because that's what it says to do on the mark scheme, but they allow you to point towards that positively charged carbon. If you pointed it somewhere else on the aromatic ring, you would lose the mark, because obviously if you pointed it into the aromatic ring, for example, as the reverse of electrophilic substitution, that would be wrong, because it doesn't actually go into the ring. The lone pair actually moves towards the positively charged carbon, because it's a nucleophilic substitution we're dealing with. So I'm going to re-highlight what I mean. The nucleophilic substitution is what we're talking about. So the next part says benzene can react with halogenoalkanes in the same way as with bromine, as shown in reaction 1 below. Now a few people mistakenly didn't realise that the electrophile is not bromine this time round. If you look at the question, it says in the same way as with bromine. That does not mean they're asking you to actually draw the reaction using bromine. So if you look carefully at what they've given you, you'll see that it's actually this substance, or this group here, the CH-CH3-2, that becomes the electrophile. So as with any electrophilic substitution, the group that substitutes onto the aromatic ring is what the electrophile will be. So what you've got to do is think to yourself, how do I form this particular electrophile? So what I've done is I've highlighted the electrophile species. The positive charge can be anywhere, doesn't really matter, according to the mark scheme at least. So the creation of the electrophile is an important thing. So work backwards from the highlighted group and then construct your equation around that. So let's now move on to the next part of the question, where it does actually get quite applied. So this part is where a lot of people started becoming unstuck. So I'm just going to read through the question with you and draw your attention to where it's important to remember what the question is telling you, before you can then start deciding what to put in. This is the types of reaction in B and C, so those are obviously the previous parts of the question that we've just spent some time looking at. Can be used to synthesize compound D, as shown in the flowchart below. So let's just to think about what that means. The types of reaction in B and C, in other words what you've just looked at, can be used to make compound D. So we can't see compound D on the screen, but I'll show it to you in a second, as shown in the flowchart below. So obviously you've got the beginnings of it on your screen. So if we bring the screen down, you can see the rest of the question. So they're talking about compound D here. So this is what we want to look at. So going back up to the beginning of the question, let's have a look at what each of the structures actually tell us as you go through it. So I'm essentially doing this. I'm working my way around, thinking to myself, what does it mean as I go around this reaction scheme? So I'll start by annotating in blue what each of the stages mean. So if you look at it closely, you've got a phenylamine, 1,3-diaminobenzene, and these groups here turn into these groups here. So it's obviously a diazotization, isn't it? So you've got to do a bit of recall here. It's recall and application at the same time. So you're diazotizing 1,3-diaminobenzene, but you're not then going and making an azo dye. So it draws upon your knowledge of azo dyes, but then it changes into the fluorination. Now the fluorination we've looked at in the previous page. So I've got to be a little bit careful here not to jump full into drawing azo dyes, which I saw in a few examples of people's scripts. So thinking carefully about what diazotization requires, you can now put in the reagent. Before I do that though, I'm just going to draw your attention a bit to where it says give structures for organic compounds. Why might they say organic compounds? It's obviously because there might be some non-organic reagents required. So it's two things they're hinting at there. If there's an organic reagent, draw the structure, obviously. And if there isn't an organic reagent, you don't have to draw the structure. But that also means there could be an inorganic reagent, which is where we're at right now, because the inorganic reagent that we need to diazotize a phenylamine is nitrous acid. So it makes sense to follow on by saying that you could also put in the sodium nitrite and HCl. Okay, so I saw a few people start to think that we needed fluoride-based reagents here and not that kind of thing. That's a slight misunderstanding, because if you look carefully, they've actually put it in for you. So this next part that I'm highlighting at the moment is the part you just worked out in the previous question. So they know that you understand what's going on here, so they're not asking you to say it again. So there's no reagents being asked for. They've given it to you here. Now the bit where almost everybody misunderstood, apart from one person, I think, out of the scripts that I looked at least, is the conversion of the 1,3-difluorobenzene into the structure at the bottom of the screen. So you'll notice that what I've done is I've highlighted in yellow the actual group that goes onto the benzene ring. So it's almost like a hand, isn't it? So if you actually take your right hand, and just crook the fingers and look at it, where your fingers and your thumb are, those will be the two places that go onto the benzene ring. So it's almost like a little bit, I suppose, like a bidentate ligand in a sort of very loose way. So there's two attachment points, isn't there? The attachment points are on the 5 and 6 positions. So the actual electrophile has to be based on just that bit that's been highlighted. So you keep the NH2 group, because obviously that doesn't change. But notice that they've got FeBr3, so it's an application of the idea you did at the bottom of the previous page, isn't it? So you've got the halogen carrier, that's going to react with these two bromines and remove them, leaving the electrophile. And the electrophile, just for illustrative purposes here, you don't draw the electrophile in, but the electrophile that we're trying to get hold of to do this for us is that. So I'm just going to circle that and just call it the electrophile. Just so we know what's going on. So that's what you need to be thinking about. So this next part almost everybody got. The last part, the bottom of the page, is easy. So let's draw the page down. Right. So we're almost there. There's 3 marks available in total, so obviously 1 mark for each of the correct reagents. This is our 3rd mark we're getting now. So let's now have a look at the compound we're supposed to make. So what I've attempted to do here is to highlight the different parts of compound D that you need to be thinking about. So highlighted in yellow is what we created in the previous stage. So in other words, I'm just going to highlight what I'm talking about here. And in purple is the group that's actually reacted with that. So the functional group that's reacting on the yellow highlighted compound that we've just made is the NH2 group. So if it's an NH2 group that's reacting, whatever is coming in to react with it to create the circled amide link would have to have a COOH on it somewhere. So all you have to do here, and I think most people managed it, is to actually take the purple part and convert the end bit with the that's circled into a COOH, which will give you something like that. I suppose the only thing to watch out for at this point is making sure that your positioning on the aromatic ring is appropriate. You don't suddenly put things on the wrong place. I don't think I saw any examples of that, but it would be an easy mistake to make at this point after been doing some fairly heavy duty thinking earlier on in this question. Right, so let's now go on to the next question, which is about a fairly straightforward idea called percentage yield. So we're still talking about compound D, but this time we're switching our emphasis away from the chemistry onto the percentage yield, a little bit of mathematics. So as with any calculation, don't take it the wrong way, but obviously I'm going to highlight where it says calculate, because it's a slight shift, isn't it, in your mindset away from recall and deduction based on your organic chemistry to calculation based on maths. It's actually a different part of your brain that's engaging at this point. So I'm not telling you that it's a calculation, you can obviously tell that for yourself, but I'm just highlighting that. That's the key word that will now tell your mind to think, okay, now I'm doing some maths. So what does that mean in terms of chemistry? It means start looking for the data, then the moles, then you can take it from there, data moles equation, moles answer. You might recall that from last year when we were first teaching you about chemistry calculations and titrations. Okay, so now we know we're in calculation mode. It says that 1.73 grams of compound D was prepared. In other words, you have 1.73 grams of the compound on the right. So I'm going to put in the ideas that should be springing to mind in blue. So take anything that's in blue to mean deductive thinking. So basically, the writing in blue is what you're trying to do. You make 1.73 grams of compound D, and from that you can deduce how much 1,3-diaminobenzene was used. Sorry, not produced, I'll just change that slightly. So what mass of 1,3-diaminobenzene was used given a 40% yield? So let's collect all the information that we've got. Well, we know that 1.73 grams was made of compound D. We know that we had a percentage yield of 40%. We know that the MR of compound D was 346.0. Now at this point we can do another deduction, can't we? If we're given the MR and we're given masses, then it's no surprise that we can work out the moles of D. So that's your way in. So let's do that first of all. So that's our first mark. And what we've got to look at is the number of moles of diaminobenzene that would be needed, given that that's the number of moles of D that's produced. So the next thing to do is to recognize that the mole ratio between D and 1,3-diaminobenzene is 1 to 1. So therefore, if you had 100% yield, you'd be expecting to get 0.00500 moles. Also, use 0.00500 moles of 1,3-diaminobenzene. So now we've worked out that with a 40% yield, you'd get 0.00125 moles. We now have to work out how many moles of 1,3-diaminobenzene was actually used up, and then convert that into a mass, because they actually want the mass, not the moles. So we know the moles of 1,3-diaminobenzene that was used. That needs to be converted to mass. So your final answer will be 1.35 grams. And you may have also spotted a discrepancy between the highlighted 0.00125 and the 0.0125. That's an error on my part, so I'm sorry about that. I'm just going to go back and slightly change what should be 0.0125 moles, like that. Okay, apologies for that slight error. Let's now go on to the next page. So on this one here, it says that compound D has been developed as a possible drug to be used to treat heart conditions, and it also mentions that only 25% of the dose was effective, and it actually mentions it twice. So can you see, if I have another look at the question, can you see how it actually says 25% of the dose was effective? Has actually been said twice. So what that would mean is they really want you to use that in your answer. So the first mark would be for making use of the 25% idea. So compound D has 2 chiral carbons. If each chiral carbon can have 2 possible stereoisomers, then it means a total of 4 possible enantiomers could be produced. If only one of those is 100% effective on treating the heart condition, then if you don't do something about that 25%, if you don't do something about the fact that there's 2 chiral carbons, meaning 4 possibilities, your dose will only be 25% effective. This means that 75% of your dose could either be toxic, at worst, or at best ineffective and therefore wasteful of resources, and make the drug more expensive, and you'd have to take more of it to get the same effect on your heart condition. So to get around this problem, you'd use things like chiral pool synthesis, bacterial or enzymatic synthesis. You could use biological methods, or you could use chiral catalysts. So in other words, think about what different techniques could be employed to stop the production of ineffective or toxic stereoisomers in the first place. So the second and third marks, the third mark would be for the prevention techniques. 2 marks would be for, firstly, saying that there's 2 chiral carbons, and then secondly saying that there's 4 possible stereoisomers, so making that deduction. So that's how I'd suggest constructing the answer. Okay, so we'll do the next question in a sec. So if you want to make sure that you've annotated your answer and put in anything extra that you could have added, and then we'll move on. So this question is about amino acids, obviously, and you've probably come across past paper questions that have serine in them. It's been in several papers before. It's an alpha amino acid, so therefore what you need to take from that is that it's got a very simple, the simplest form of amino acid, in other words. So it has that sort of structure with an amine group on one side, a carboxylic acid group on the other, a central carbon, an R group and an H. So obviously the central carbon is chiral. But this isn't about chirality, this question. It's another reaction scheme, isn't it? So if we have a look at what we've got functional groups on serine. There's 2 of them. One is the carboxylic acid group and one is the alcohol group. But what you're being asked is whether it will react with, or in what way will it react with sodium carbonate. So we know that the carboxylic acid group is the only one that will react with that. So it should be a fairly straightforward process of reacting the sodium carbonate with the carboxylic acid to make a sodium carboxylate salt. So in the mark scheme they don't put the charges, they're not absolutely essential, but it just shows the point in the overall molecule where there's an ionic bond. So if we now have a look at the next reaction, reaction 2, I'm going to remove some of the highlights and now bring your attention to that part there. So here we've got the alcohol group reacting instead. Beg your pardon, we don't have the alcohol group reacting, let me just remove that. We still have the carboxylic acid group reacting, but it's reacting with an alcohol. And you've also got H2O. You've also got to bear in mind that it's acidic conditions you're working with. The presence of the acid has 2 consequences. Obviously it's required for the esterification to take place when the alcohol group on the compound at the bottom of the screen and the carboxylic acid on serine actually react. But also it means that you now have acid conditions. And if you have acid conditions, that now means that the NH2 could react with the excess protons. So quite a lot of people miss this third mark that's available, because you can see that there's 3 marks available. So 1 mark is for the product of reaction 1, 1 mark is for the bulk of the correct structure of the product of reaction 2. But I'll draw it in a second and you'll see that there's actually 2 slight changes that happen. The most obvious one is the creation of an ester, which the vast majority of people got. So if you look closely, you'll see that there's actually an NH3 plus that's now formed as a consequence of the NH2 group, the amine group on the amino acid in the original serine, now actually reacting with the protons from the sulfuric acid. So the next part is quite straightforward. All you have to do here is recognise that there's an ester. Now I've just realised I haven't quite drawn it correctly, so I'm just going to go and change it. I've just slightly corrected that, so now what we can look at is where it says suggested use for the organic compound formed. We're looking at the fact that we have an ester. So now we can put down that it's used for either flavourings or perfumes. These are the standard general uses. Occasionally esters are used for solvents, but not often enough for it to be main use. So I'd stick to things like perfumes, flavourings, fragrances, things like that. So any one of those three things would be fine. So to do the next bit of the question, we have to actually move it down. The actual next bit of the question is on the next page of the script, so you need to have the 2 pages open for it to make full sense. But I'm going to answer the next part of the question on this page, so then when you see the next page on the screen, it'll make sense why I've put the answers in there. So the next 3 things that it asks over the page are the reaction conditions and reagents for reaction 3, and the types of reactions that reaction 4 and reaction 5 are. So to do this, we have to just look at the reaction scheme, follow it through, and see what actually changes as we go. So in the first change, we go from having a Cl to an NH2. So both Cl and NH2 behave as nucleophiles when they're individual functional groups. So therefore, it would be a simple case of nucleophilic substitution using a source of NH2, which would be the NH3 nucleophile really. So it's basically ammonia dissolved in warm ethanol, or something along those lines, to suggest that that combination and those conditions are used. So to work out what kind of reaction 4 is, you need to check what's actually changed. So the NH2 group is still there, so it's not that anymore. So it must be the alcohol group changing into a carboxylic acid, which is obviously an oxidation. And doing the same thing for reaction 5, what happens this time is an ester group changes into an alcohol group, which is a hydrolysis. So just to clarify what the colour coding means, the reaction conditions and reagents required for the 2 functional groups in blue, highlighted in blue, to change from chloro group into an amine is the ammonia dissolved in warm ethanol. The type of reaction to change the alcohol group, highlighted in yellow, into the carboxylic acid group in reaction 4 is an oxidation. And the type of reaction to change the ester group, highlighted in purple, into the alcohol group in serine, also highlighted in purple at the end of the series of reactions, is a hydrolysis. So the key piece of advice here to work this out is, in each stage, look carefully for what's changed. So providing you've done enough revision and have gone and remembered and recalled using flashcards, etc., the reaction conditions from the specification, so long as you look at what changes in each stage of a series of reactions, it's really easy then to predict the reaction types, but also reactions and conditions, reagents and conditions, depending on what the question is asking you. So when we go to the next screen, the answers will be in the right places for the first part, because that's the bit we've just discussed here on this screen. So what I'll be doing is going straight down to the part where it asks you to predict the structures of some polymers, which is a separate part of the question. Okay, so the next part talks about a new compound different to serine. So I'm going to move the page up because this bit of the question is quite deductive and caught a fair few people out. It's not incredibly easy, but a bit of thinking here. So I'll take a bit of time trying to talk you through this. So it says compound E is it can be oxidized by tolerance reagents. There's three pieces of information. It's one of two optical isomers. It can be oxidized by tolerance reagent. And it can be oxidized to an amino acid. The reason I colour-coded those three pieces of information is so I can put down the side what each of them actually means and how you can use that to deduce a little bit about what to put. So each specific piece of information in that sentence actually tells you quite a lot. So you can use those pieces of information to work on what you think compound E might be. Now the next thing to look at is that in compound E, the ratio of carbon to hydrogen must mean that it's not saturated, it's unsaturated. So adding up all of the information that we've got, it's unsaturated, it's an aldehyde, it's got a chiral carbon, it's got 4 carbons, 7 hydrogens, 1 nitrogen, 1 oxygen, that's what we come up with. So each section of that molecule can be arrived at by one of those clues. So then it tells you that it's oxidized by tolerance reagent to form an amino acid F. Now obviously an amino acid has to have an acid group and an amine group. We've already got the amine group in E. An aldehyde will oxidize under the influence of tolerance reagent to a carboxylic acid. So it's quite easy now to deduce what F is going to be. So F is an oxidation product of E, and it also happens to be an amino acid, an alpha amino acid, because it follows the template that I've drawn in purple in the top right hand corner. So then it says draw repeat units of polymer G and polymer H. So let's have a look at what that means. Let's go back to the question, and you can see that polymer G has the empirical formula C4H7NO2. Polymer H has the empirical formula C4H5NO. Now this next bit's really subtle, because if you look carefully at the difference in the two empirical formulae between G and H, you'll see that there's actually a difference of H2O between them. So the one that has 1 less oxygen and 2 less hydrogens, H in other words, must be a condensation polymer. So that now tells you what's actually going to happen when amino acid F is polymerized. So if we've worked out that H is a condensation polymer, let's do that bit first. So notice what I've done is I've created an amide linkage between the NH2 of one monomer and the COOH of another. So on the left hand side it's part of an amide linkage with the NH, and on the right hand side it's part of the other amide linkage with the C double bond O. I've left the double bond in there because it's not an addition polymer, that doesn't get touched. It's a condensation polymer because the empirical formula is C4H5NO, H2O less than C4H7NO2. The other polymer, G, must be a different type of polymer, which is an addition polymer, so that would require me to break the C double C bond and leave the rest of the molecule alone. So you need to also say how F forms G and H. So saying that one is addition polymerization, the other one is a condensation polymer, will cover you for that. So we've drawn the repeat units, we've suggested the structures, and we've covered all the points we want us to cover. So let's go into the next part of the question. It says polyglutamic acid is the polymer of the amino acid glutamic acid. This bit should be really straightforward. I think most people manage to get this without any difficulty. This is an example of where the question can suddenly get quite easy and other parts of the paper can be quite difficult. So it's another part of the mindset, isn't it, to be prepared to accept that if there's an easy question, that's because it is an easy question, not because you haven't spotted something. That in itself can be sometimes quite challenging when you're primed to expect difficult questions by this stage. So like I've just mentioned, that part of the question is fairly straightforward. And the next part of the question is where it gets a little trickier. So I'm going to bring the page down a bit. I'm going to leave the structure of glutamic acid there because you need to have it to understand what we're going to do next. And the really key part of this question is the fact that no polymer was found in the product mixture. This has a specific meaning when we're looking at amino acid type molecules. So you need to make a little bit of a jump here, and that jump means to accept that there might be other ways in which the functional groups might react with each other, as opposed to just forming a big long chain. Now the idea of them forming a chain is what you'd expect if they polymerize, but it says that there's no polymer found in the reaction mixture, or product mixture. So there has to be something else going on instead. So it said the student isolated the two major compounds in the mixture. That means something has reacted. It means that it doesn't just not reacted, something has happened chemically. So the only thing you can arrive at really is that a non-polymer product is formed. The only way that that could work between the functional groups that you've got on your glutamic acid is ring structures being formed somehow, or what we call cyclization. You can get cyclic esters, for example, if you have an alcohol group and a carboxylic acid group on different ends of the same molecule. They can reach round and react with each other. So there's nothing to stop you trying something like that here. In fact, that's what they're after. So this is one option where one molecule of glutamic acid actually has two different functional groups reacting with each other. And there's another option is where two glutamic acid molecules do something similar but slightly overlap. So that's the kind of thing they're after for the second one. So if we were to highlight the specific parts of that, I'm going to highlight one glutamic acid molecule, and then I'm going to highlight another one, different colour. So two glutamic acid molecules interacting a bit like that. So the key thing here is that you've shown that you understand cyclization is taking place. They're quite flexible, I think, in the mark scheme here to show the different ways in which cyclization could occur. For example, you could get a three-membered ring happening over here somewhere. That you could get partial cyclization over there. So any attempt to show that a ring structure is formed, so in other words, you're understanding and realizing that this is possible here, what I'm highlighting in purple. So once you can see the possibility of functional groups on the same molecule reacting with each other, then that also opens up the possibility of new ways of deducing answers to applied questions such as this one. And This does happen quite a lot. You sometimes see this on RPA papers. Looking back over the past 7 years or so, there's quite a few examples where this pops up, so it's well worth bearing in mind for future reference. So then the next part of the question, but just before I do that, I just realised it's also important to look at the other clue that I've given you, and that's the m over z values. So you need to double check that what you're writing actually matches each of those. So there is flexibility provided you actually match the m over z values to what they give you. So two things just to recap. Make sure there's a ring structure somewhere, because that then takes account of the fact no polymer is produced. And then make sure the compound that you're drawing matches the m over z value that they give you. It says polymer J has been recently developed by scientists, and the repeat unit of polymer J is shown below. And they want the functional groups. So obviously one functional group is going to be the amide group, and the other functional group is going to be the ester group. So in this particular section of polymer, the ester group isn't sort of fully drawn at one end, it's partially at one end and the other part of it is at the other end. To be ester and amide. Now the reason that you have to have both to get 1 mark is because it says what functional groups, so it's plural, not what functional groups, so therefore there's more than one that they want. Okay, so then it says 2 different monomers react to form polymer J. And it says draw the structure of the 2 monomers, so it's obviously going to be a diol and also an amino acid. Sorry, a dicarboxylic acid on the one hand and a amino acid on the other. So all you have to do is take the number of carbons that are present and use them to deduce the type of molecule we're looking at. So on the script that I looked at, most people were successful at getting this down. I'm just going to put the hydrogens in because I realised I've just missed them out. It's always a good idea to make sure if you're doing a display formula that all of the hydrogens get put in. Okay, so now let's move the page down to look at the last part of the question. So it says polymer J was used in hairspray can also be washed away easily with hot water. Now there's another example where they say the same thing twice. If you look, that's a really heavy hint as to what to base your answer on. So think about water. Water is neutral, but sometimes it can be slightly acidic or maybe slightly alkaline. The water that comes out of the tap is probably going to be slightly acidic or slightly alkaline because it's not distilled, it contains ions. So therefore, if you have a slight alkaline or acidic bias to your water, that's going to help the polymer hydrolyze, and there we have it, that's what they're after. So although at face value it seems like a fairly obvious answer, I'd steer away from just saying it's soluble in water. I'd say something more chemically accurate. It's soluble in water because it hydrolyzes, or because there's hydrogen bonding between the amide links and the water molecules. So go a little bit deeper, because it is an A2 question after all. So let's go on to the last question, which is about NMR. And a lot of people found this one a bit tricky. Now this first part, this first page, this was just pure recall of facts. There really wasn't any reason to not get these few questions here. It's the next page where it gets you to analyse precipitate L, where it gets a bit difficult. So I'm just going to simply put the answers down without talking about them, because they should literally be things that are lifted out of your mind, which in turn would have learnt them from the textbook and notes. So all of those 3 things can be easily taken from the textbook. So I'm going to bring the page down and have a look at the last part of this particular page. So it says that the carbon-13 NMR spectrum is L. So L is going to be the orange precipitate, top right-hand corner, is shown below. It says how many different carbon environments, and it even tells you what that means, types of carbon are present in a molecule of compound L. All you have to do is count the number of peaks. So there's, if you didn't get this, and I'm sorry, but that was just carelessness. You just literally count the peaks and that's it. So from what I can recall, everybody got that one. So that was a nice easy one. So let's now go over the page. This is where it gets a bit tricky. Not a bit tricky, quite applied. It's doable, but you just have to have your wits about you a little bit. So what I'm going to attempt to do is try and clear it up and take you through it to enable you to see how it could be done. And most importantly, to see how you can do something similar in a new paper, because each paper will have a new compound that you won't have seen before. So the NMR questions do tend to be quite applied. So there's not really such thing as memorising your way through an individual NMR question. There's a technique for how to lay out your analysis, which I'll come to in a second, but applying it requires some thought on the day. Okay, so I'll try and make the page a little bit smaller so I can fit my analysis in, and you can have the diagrams to refer it to as I talk through it. So as I go through it, I'll try and pop some notes down the right hand side in that column that's now been created, just to help you see how maybe it could have been deduced at the time. So I'm assuming that you've got your data sheet with you, because it's difficult for me to have two separate files up at the same time on the screen. So this file, which is obviously the paper itself, you need to have your data sheet with you for this to make full sense. So they want you to identify orange precipitate L. I'm just going to highlight that bit there so we know what we're looking at. So just so there's no sort of confusion at all, I'm even going to draw a box around it. That's what we're looking at. Okay, so what I'm going to do is do a table and then try and talk through it to hopefully see how you can see how it could be done. That's the way to lay your analysis out to start picking up some of the marks. It's not quite finished yet. I ran out of room at the bottom, so I'm just going to bring the page down. But before I do that, I just want to draw your attention to the purple highlighted part of the question. And I've written in the analysis for that particular part, that particular peak, which is going to be this one here. So that's already provided in the question, so even if you put that in your analysis, you don't get a mark for it. But it's part of the overall picture, so I'll leave it in there. It's just moving it up slightly so I can have some room to add it in. So 4 marks are available for the straight analysis that we wrote in red. And a 5th mark is available for bringing together 2 of the peaks, 2 of the shifts, to deduce that you'd have a CH2-CH3 group. So they always ask you as well, in part of the mark scheme, to try and bring 2 of the shifts together somehow and put them into a slightly larger part of the molecule. So now let's try and have a go at the structure. So I'm assuming that you've got this copied down and maybe slightly altered yours, because I won't be able to come back to this on the clip. So I'll just put that down as a note at the top before we go. So I've just laid out what I've just mentioned there. So let's now go and have a look at how the structure itself might be worked out. Okay, I'm just going to bring the page up. Again, because that's where we want to draw in our structures. So So what I'll try and do is add some notes on the right hand side here as well to flesh out what I'm saying. So that's the structure of compound L. What I'm going to do is I'm going to work backwards from that structure to show you how you could have worked each part out. So the part that's highlighted in purple you knew about already. So what they're interested in is the remainder. So the part that's highlighted in blue can be worked out from the fact that there's a singlet at 1.7 parts per million that has 3 protons in that environment. So it's a CH3 attached to a C double bond N. The C double bond N has no protons attached to it, so it's a singlet. Like that. Okay, the part that's highlighted in grey, you've already worked out that there's a CH3CH2 because you brought 2 of the previous analysis of the chemical shifts together. That was covered on the previous screen. The CH3CH2 can be at the bottom left hand corner of the box. So why the extra aromatic ring? So if you go back to the analysis you did, you'll see that the proton environment for an aromatic ring with a hydrogen coming off it means that it has an integration ratio of 7. There's only 6 protons present in one aromatic ring, so it must mean there's 2 aromatic rings. This also pulls in the carbon NMR analysis that you did to show that there were 14 carbon environments. So now you can count up the carbon environments. So if you have a look at them and count them up, you can see that the carbon NMR spectrum also matches as well. So I just want to say at this stage, I know it's all very well me saying, working backwards from the answer, how could you have actually got this from scratch? The part that's actually in purple, like I've said already, is the bit that you know about already, so some of it's been done for you. The marks are actually for working out what R1 and R2 are. In other words, the blue and the grey parts of the molecule that have been shaded. So if you work through it carefully, you should enable you to see something along those lines. So compound K is easy because all you really have to do is look at what happens when the C double bond N is formed when the C double bond O of an aldehyde, which was your compound K, is actually produced. So what you do is you take the purple bit out, because that's what's actually added on. You take the carbon number 7, if you look carefully at the top, and then you take the purple part off and just put a carbon double bond oxygen instead. That's it. So there were ECF points, error carried forward points, available here, even if you didn't get compound L correct. If you did the correct working backwards to what the compound K might be like, and doing that deduction that we just looked at, then that should be fine. Okay, so the thing to take from this paper is what skills could you use? So you're probably aware already of reading the question. But what exactly does that mean? It means looking for clues. It means using earlier parts that you've already worked out because they were a bit easier in your efforts to work out the harder parts later on. And if something is stated twice in the question, I think we've come across this a couple of times during this paper, if something's stated twice in the question, you definitely use it in your answer. And finally, it leaves me to wish you good luck on the real thing. Please try and think about some of these skills and put them into action. Okay, so thanks for listening, and all the best when you take your paper.